everyone, and welcome back to our Tuesday walkthrough, second part on supervised learning, this time naive Bayes. Let's get to it. As a reminder, we are working on our classification dataset. This time around, it is the insurance dataset. We have imported the insurance dataset previously. We've also imported NumPy, Pandas, Matplotlib, SciPy, and stats models. Let's first find out what naive Bayes is all about.
Now, imagine we receive normal messages from friends and family. And we also receive spam, unwanted messages that are usually scams or unsolicited advertisements. And we wanted to filter out the spam messages. So, the first thing we do is make a histogram of all the words that occur in the normal messages from friends and family. We can use the histogram to calculate the probabilities of seeing each word, given that it was in a normal message. For example, the probability we see the word dear, given that we saw it in a normal message, is 8. The total number of times dear occurred in normal messages, divided by 17, the total number of words in all of the normal messages. And that gives us 0.47. So let's put that over the word dear so we don't forget it. Likewise, the probability that we see the word friend, given that we saw it in a normal message, is 5. The total number of times friend occurred in normal messages, divided by 17, the total number of words in all of the normal messages. And that gives us 0.29. So let's put that over the word friend so we don't forget it. Likewise, the probability that we see the word lunch, given that it is in a normal message, is 0.18. And the probability that we see the word money, given that it is in a normal message, is 0.06. Now we make a histogram of all the words that occur in the spam and calculate the probability of seeing the word dear, given that we saw it in the spam. And that is 2, the number of times we saw dear in the spam, divided by 7, the total number of words in the spam. And that gives us 0.29. Likewise, we calculate the probability of seeing the remaining words given that they were in the spam. Now, because these histograms are taking up a lot of space, let's get rid of them, but keep the probabilities. Now, imagine we got a new message that said, "Dear friend," and we want to decide if it is a normal message or spam. We start with an initial guess about the probability that any message, regardless of what it says, is a normal message. This guess can be any probability that we want, but a common guess is estimated from the training data. For example, since 8 of the 12 messages are normal messages, our initial guess will be 0.67. So let's put that under the normal messages so we don't forget it. The initial guess that we observe a normal message is called a prior probability. Now we multiply the initial guess by the probability that the word dear occurs in a normal message, and the probability that the word friend occurs in a normal message. Now we just plug in the values that we worked out earlier and do the math. Bip boop bip boop bip. And we get 0.09. We can think of 0.09 as the score that dear friend gets if it is a normal message. However, technically, it is proportional to the probability that the message is normal, given that it says dear friend. So let's put that on top of the normal messages so we don't forget. Now, just like we did before, we start with an initial guess about the probability that any message, regardless of what it says, is spam. And just like before, the guess can be any probability we want, but a common guess is estimated from the training data. And since 4 of the 12 messages are spam, our initial guess will be 0.33. So let's put that under the spam so we don't forget it. Now we multiply that initial guess by the probability that the word dear occurs in spam, and the probability that the word friend occurs in spam. Now we just plugged in the values that we worked out earlier and do the math. Bip, boop, bip, boop, bip, and we get 0.01. Like before, we can think of 0.01 as the score that dear friend gets if it is spam. However, technically, it is proportional to the probability that the message is spam given that it says dear friend. And because the score we got for normal message, 0.09, is greater than the score we got for spam, 0.01, we will decide that dear friend is a normal message.
All right, so you just learned how multinomial naive Bayes works. We are going to use Gaussian naive Bayes in our computations, which is very similar, does the same job, almost the same. If you would like to understand more detail about how it is different, please click on this link. This will get you to the DataCamp blog post about naive Bayes and classification with naive Bayes, the naive Bayes formula, etc. And it will walk you through a Gaussian example. We are going to continue with our workbook walkthrough. So the first thing we're going to do for naive Bayes is we're going to set up the environment. From our sklearn naive Bayes, we're going to import the Gaussian naive Bayes. I wouldn't have to re-import the accuracy score. I've already imported it above, but whatever. The next thing is we're going to take a look at our insurance data set. I'm going to use my insurance 2 data set, which is already the smaller one with just numeric inputs and with my region class attribute on the very right side. So that is still in place. I'm going to double check the data types to make sure I don't have any surprises here in what I assume is numeric, and it still is numeric. And then region is categorical. That's exactly what I want. So now let's set up the training and the test sets. We're going to now set up our training and our test sets with a slightly different test size. We're going to make our training set 80% and our test set 20%. Let's see if we get a model that's a little bit better than what we had with the k nearest neighbor of 1 and k nearest neighbor of 5. So for that, I'm going to set the test size to 0.2. And I'm going to use my train test split here on my insurance 2 data set. And then I'm going to print my insurance train and my insurance test. And as we can see here, the dimensions are right here. 5 columns, 1070 rows in my training set, 5 columns, 268 rows in my test set. Very good. Okay. In order to continue working with my data set, I'm going to have to convert my insurance training and my insurance test sets into NumPy arrays. That is the next thing I'm going to do. So here I'm going to call this insurance train NP here, and then my NumPy array is going to be pulling from inst train and from inst test here. So inst test being this, inst train being this. So all I'm doing is converting these into NumPy arrays. Now that I'm done with my training and my test sets and with my pre-processing, I can go on to building the model. This is a bit anticlimactic. I'm going to call my Gaussian naive Bayes function, and I'm going to put that into insurance naive Bayes. And then I'm going to apply my Gaussian naive Bayes function with .fit. Remember, we use .fit to apply our function to our training set. Now, there is a problem with our training set because look at this here. We have not split our x's, that's our inputs, from our y, which is our class attribute here, region. we need to do that. We can either do that separately, or we can do that inside of our code. And I'm going to show you now how to do that. So inside our fit function, I'm going to use my insurance train data set, but I'm going to have to drop the region column here. So I'm going to drop region, axis equals 1, which is the column, and I'm going to put that into insurance train region. And that gives me the Gaussian naive Bayes. And now we're going to do exactly what we did with our k-nearest neighbor. We're going to calculate our y-pred, which means we're going to calculate our insurance predictions by using our insurance naive Bayes model that we've built up here. But we're not going to fit it this time because we've already fitted it. We've already trained it. This time we're going to use it. So this means we're going to use .predict. And we're going to use our insurance test data frame. Now, if we look at insurance test here, you will see the same problem that we had with insurance train. We have 5 attributes here when we should have 4 attributes, our x's, and then our y here, which is region. So we're going to drop that as well here. So now we can calculate the accuracy score on insurance test region and on our insurance predictions. And our accuracy score comes out to be 0.34. So despite the fact that we have increased our training size to make our model more accurate from granted 75% or 67% to 80%, we are really not getting much more accuracy here. Previously, we had something around 34%, 33%. So the difference is negligible. Well, okay, let's take a look at our insurance predictions here. These are the insurance predictions. And let's compare them. We're going to do exactly the same thing that we did before, where we are going to use our insurance predictions and we're going to put them side by side with the insurance test region attribute. And our insurance predictions are going to go on the left side. Our actual, real, original values that we know are true from our insurance test data set are going to go on the right side. And here is what we're seeing, northwest, northwest. Well, that's a good start. But then we're seeing here southwest predicted and northwest is really the truth. Northwest is the truth here that was predicted as southeast. Northeast is the truth that was predicted as southwest. So really, there really isn't that much of a quality improvement. We can already see that. So now it's your turn to build a confusion matrix. You've already seen how to do that previously in the k-nearest neighbor section. And it's your turn also to build a classification report. You've also seen that in the k-nearest neighbor section. Then I'm asking you to compare the results from the confusion matrices and the classification reports between k-nearest neighbor and naive Bayes. Is there a difference? Does it really matter that we've adjusted the training set size and the test set size, or does it not matter? Right? And how valid do you think are the results at all? So do you think that with the data that we have, can we actually reliably predict the region where somebody comes from based on their age, their BMI, the number of children that they have, and the number of previous insurance charges? That is the really big question here, and that is the critical thinking portion of this exercise. Was this thing that we did here a nice thought exercise, or is it usable? What do you think? Thank you.